Exercise 12, 14. There we go. Hello, everyone. Dum-de-dum. So I'm waiting for a few more viewers, and then I'll get started. Waiting for a couple more people to join. Having my toast with peanut butter and honey. Okay. We have enough people to get started. All right. Got to get my notes out. All right. So for the next 2 days, we are going to be, or the next 2 lessons, I should say, we are going to be talking about data transmission. Over networks. So that's the topic of today's lesson and Thursday's lesson. So let's just talk about what do we want to achieve, or what must data transmission achieve in order to be considered successful. Okay. So I've just got some bullet points here. The first thing is you have to achieve data integrity. So data integrity means that the data that's being sent over the network, so let's say sent data, is not altered. And it could be altered either maliciously by, someone who's trying to someone who's trying to steal information, or or money even. Or it could be altered just by interference, just random bit flips as the data is transmitted. So we want to have as much data integrity as possible. We also need to have source integrity. That means that the sender of the data is verified. Okay, so that's really important, that the source where the data is coming from is not altered. It's kind of like, let's say that you sent a request to your bank that you are going to, be receiving $25,000 from someone, and so they're going to give you $25,000. But then I steal your message and make it look like I was the one who sent the message to the bank, and then I received the $25,000. You get what I'm saying? So the source is important. You don't want someone to receive money when they shouldn't be, things of that nature. Flow control is one thing we want to achieve. So flow control means that how is traffic handled on the network? So there's a couple of like subtopics in flow control. One is congestion management. So if the demands on the network are greater than the network can handle, then how do we sort of resolve the conflicts? Okay, how do we get ourselves, it's kind of like if you have a traffic jam, how do we manage how the traffic jam is going to sort itself out? Okay, so that's congestion management. You can also have what are called deadlocks. So you need to have deadlock prevention. So what is a deadlock? A deadlock is when two computers are each waiting for the other to respond to them. So they're neither one is actively sending messages to the other. They're both waiting for a message, and so nothing is going to happen because they're both waiting. Okay, so you need to figure out how to prevent deadlocks. You need to do error checking. Okay, so we already dealt with this in the last assignment that I gave you guys. It was about error. We had a parity bit in our message. So we talked about parity bits and how those can check for errors. There are lots of other ways of checking for errors, but we need to have some method of checking for errors, and we also need to have some method of error correction. Okay, so do we say resend the data, or if the message has an error, is there some way that we can figure out what the error was and just correct it ourselves? Okay, so there are just different things we have to think about. Okay, so if we took the IB exam, they might ask you, what does one of these terms mean? So now you know. Okay. So I want to talk about the speed of transmission of data. Okay. So speed of transmission is measured in BPS. So that stands for bits per second. So how many ones or zeros are being sent per second? You can also have speeds that are ranging in the kbps, that's kilobits per second, so that would be thousands of bits per second. Mbps, megabits per second, so that's millions of bits per second. Gbps, I don't know if we can achieve Gbps. Actually, I saw something interesting that if you have a huge file that you need to send from point A to point B over a network, if the network speed is not fast enough, it can sometimes be better to put the data onto a hard drive and to physically mail the hard drive, which I think is really funny. So I know this has happened before where it's like it happens in science projects where the data that is going to be analyzed is like extremely huge. And so rather than send the data over a network, they just put it all on a hard drive and just mail the hard drive. And that's faster and cheaper. I wonder, what are your guys' connection speeds? Do you ever do the speed test? Usually your upload speed is a lot slower than your download speed because of the properties of your router. Okay. Maybe we should do that in the Zoom room. We should all do an internet speed test. That'd be fun. Let's do that. Okay, so what are some things that affect the transmission of data? So the first thing is the network bandwidth. Okay, so the network bandwidth is the theoretical upper limit of transmission speed. So that basically is determined by the technology that you're using. Okay. Whether it's, we're going to talk more about these, but are you using coaxial cables or fiber optic cables or whatever? Okay, so that obviously determines the speed of transmission, but there are a lot of other things. Okay, one thing that can affect it is interference. Okay, so interference mean the things that are transmitted over the network are being changed. So that's not part of network bandwidth because the theoretical upper limit is talking about if there was no interference whatsoever. But interference is going to make it so that messages need to be resent, that we need to have error checking. And as we know, error checking makes the message longer. It makes it a bigger file size. So there are all these different things, okay? Malware can affect it. The speed of the computers. On the network. So if we think about the computers on the network, they have to basically store or access the message. If a computer is going to send a message, it has to access the message in memory and then transmit it, okay? If it's receiving a message, it has to put it into memory. So how fast the computer can transfer the bits that it's receiving into its memory determines the rate of transmission, because if you send the information too fast, the computer can't do anything with it, okay? And then this also, so this has to do more with memory, but then also just the straight up CPU speed determines how fast the message can sort of be interpreted. Okay, so that affects the transmission speed. Of course, the size of the files is going to determine, if you're sending a huge file, it takes longer to send than a short file. The number of devices on the network. Okay. So this is going to have to do with flow control. So if you have a lot of devices on the network, then you might have a flow control problem where you have to manage the congestion in the network, and that slows down the speed of transmission. And so these are kind of some of the highlights, okay? Now, when we talk about all this stuff, so we sort of have the bandwidth, which is the theoretical upper limit, okay? So, if you buy internet from your ISP and they give you that number, it might be 100 Mbps or whatever, they're giving you the bandwidth. That's the theoretical upper limit. But as you know, they might, when you actually download things, you're not going to get the number that's quoted, okay? All right? So the actual rate at which information is being transferred is called throughput. So it's not the upper limit, it's the actual rate. Okay. And as you know, when we send the data, we have to have things like parity bits, and there's all kinds of extra information, like we have to include the destination of the file. Well, that has to be contained in the message itself, right? It has to, just like when you send a letter to someone, a snail mail, it has to have the address of the person, right? So that there's more than just the message itself that is being sent over the network, okay? And so you have this thing called good put, which is the rate of transmission of the actual data. I should say of usable data. You're not really using. So when you send a message, you're not going to actually use the parity bit for anything. You're not going to actually use the address. Okay, so there's all that extra information counts as part of the throughput, but it doesn't count as part of the good put. Okay, so the good put is the bits per second of actual message that are being sent. Okay. Now, oftentimes these are affected by a bottleneck. Okay, so as I was mentioning, all of these things affect the speed of transmission, and usually one of them is going to be the slowest, and so it's going to be the thing that sort of holds up the whole process the most, okay? So for example, if you have a really fast network, but you have really slow computers, then the speed of the computers is going to be the bottleneck. Okay, so you want to think about bottlenecks when you're paying for something too. It's like why pay for really fast internet if you have a really slow computer? You know what I mean? So it's kind of like those two things have to match. Otherwise, you're going to have a bottleneck. If you have an ultra fast, if you spend all your money on an ultra fast computer that can send and process data ultra quickly, but you have really slow internet, you're not going to be able to utilize the full potential of that computer. Okay. All right. So now I'm going to talk a little bit about today's assignment, or this week's assignment. And this week's assignment is about compression of data. Okay. So when we compress so there's basically two ways of making the throughput of a network faster. One way is we could improve the physical medium of transmission so that the ones and zeros travel through the network more quickly. Another thing we could do is we could try to make the message itself smaller. So is there a way, so instead of sending the message in its complete form, we compress it so that the size of the file is smaller, okay? So you make the size of the file smaller. Okay. Before transmission. So that it's going to take less time to transmit, okay? So basically what you have is you have an original file, and then your computer will then compress the file, okay? And then it is sent over the network. Okay. And then you receive the compressed file. And then based on the rule, so there's some kind of compression algorithm, and based on that, when you have the compressed file, you can use the compressed file to reconstruct the original file, okay? So you reconstruct the file, okay? Now, so basically over here we have this is happening with the sender, and this is happening with the recipient. Okay, and then this is the internet. Now the reconstructed file. So there's a couple of different techniques. One of the ways is the reconstructed file might be identical to the original file. Okay, and if that if that is true, if the reconstructed file is identical, then that's called lossless compression. Okay, so you're able to get the exact same thing, but sometimes it's not necessary. So, for example, with images, okay, it might not be necessary to get, as you know, images have become so detailed. The images that you can take with a camera have so many pixels nowadays that the human eye can't even perceive. You lose half the pixels, your eyes don't even realize it. Okay, so it might not really be necessary to have all of those pixels exactly the same. Okay, all right. So it might. So you might have basically an approximation to the original. And if the reconstructed file is an approximation to the original, then that's called a lossy compression because you lost some of the original information. Okay? So I'm going to give you an example of how this would work. Okay? So let's think about what is an image. An image is an array of pixels. Okay, so you have this array of pixels. So I'm thinking about it as a grid. And then each pixel is a color. All right. Each pixel is a color. So how is a color there? So there's actually a class called color in Java. Okay. But anyways, a color is represented by 3 numbers. Okay. The red component, the green component, and the blue component. Okay. And each of these is an integer from 0 to 255. Okay. So 256 is 256 is 2 to the 8th. So that's 1 byte. One byte of data. So each color component is 1 byte. So the color class in Java, because it's a red component, a green component, and a blue component, it's 3 bytes of information. Okay. So what would 0, 0, 0 be? That would mean you have the absence of any color. So this would be black. Okay. What if you had 255, 255, 255? That would be, because we have an equal amount of all colors and it's all present, this would be white. What if you had, like let's say 100, 100, 100. That would be sort of like a gray. What if you had 255, 0, 0? This would be red. Like pure red, bright red. Okay? You could have something like, I don't know, 100, 0, 100. This would combine red and blue, which I believe is purple. Okay? So anyways, that's how it works. All right, so let's say you have an image that is n pixels wide and m pixels tall. All right, so the total number of pixels is going to be n times m. Okay, and then we multiply that by the number of bytes that each pixel has, so which is 3 bytes. So this entire image is going to be 3 times n times m bytes is the size of that image file. Okay. So I'm going to teach you a lossy compression algorithm. Okay. So what if we have 2 pixels and I want to compress them? So let me just come up with some numbers. Let's say 100, 50, 200. So this is pixel 1. And pixel 2, let's say is 0, comma 25, comma 150, something like that. Okay. So what I'm going to do is I'm going to get the total brightness of each pixel. Okay. By the way, how many integers does this original? So this is the uncompressed state of these 2 pixels. Okay. And I can see that it has 1, 2, 3, 4, 5, 6 integers. Okay. So this is 6 integers. Okay. So now what I'm going to do is I'm going to average these 2 colors together. Okay. So I'm going to find the average red. Okay. The average red, if I look at pixel 1, it's has a red value of 100. Pixel 2 has a red value of 0. So the average red is 100 plus 0 over 2. So that's 50. Okay. The average green is 50 plus 25 over 2. So that's 75 over 2, which is 37.5. But as we know, with integers, the fractional parts just gets truncated. So this is 37. And the average blue is going to be 200 plus 150 over 2. So 350 over 2. So that's going to be 175. Okay. So the average color of these 2 pixels is 50, 37, 175. Okay. This is the average color. All right. Now what we do is we get the brightness of each pixel. Okay. So the brightness of a pixel is the sum of its red, green, and blue, because that's basically how much light, because each pixel is literally made up out of a red, a green, and a blue. Okay. So how much light total is coming out of that pixel? Okay. So the average or the total brightness of pixel, the total for 1 is going to be 100 plus 50 plus 200 equals 350. Okay. And the total for the second pixel is 0 plus 25 plus 150. So that would be 175. Okay. So what we have is, so this stuff together is the compressed data. Okay. So notice how the compressed, now this is not a very good compression because I'm only averaging over 2 pixels. So basically the more pixels you average over, the better the compression becomes. Okay. But the compressed data, notice how it has 1, 2, 3, 4, 5 integers. Okay. So the compressed data has less, it's fewer integers. Okay. So that means it's going to be easier to send. It's not going to take as much time to send. So that's an example of a compression algorithm. So then what do we do if we want to reconstruct the original message? Okay. So let me rewrite the information. So the average color was 50, 37, 175. Pixel 1's brightness was 350. And pixel 2's brightness was 175. Okay? So now what I'm going to do is I'm going to reconstruct them. So first of all, I'm going to compute the total brightness, okay, of the average color. So the total brightness is 50 plus 37, so that's 87, 187, 262 is the total brightness. So then I can figure out how much of that total brightness is red, how much of that total brightness is green, how much of that total brightness is blue. So I could do that by computing the red weight. So the red weight is going to be 50 out of 262. Then there's a green weight. How much of the average color is green? That's going to be 37 out of 262. And then there's going to be a blue weight, which is how much of that original color is blue, or that average color is blue. Which is 175 out of 262. All right, so let me compute these numbers. 50 over 262 is 0.19. 37 over 262 is 0.14. And then 375 over 262 is 0.67. So we can see that these 2 pixels were mostly blue because that has the largest weight. So now let's reconstruct pixel 1. Okay, so if we want to know how much so we have a total brightness of 350, okay, and we know that 19% of that total brightness is red, okay, so I do 350 times 0.19, and I get 66.5, okay, then I have 350 times, and then I know that 14% of that brightness is green, so I multiply it by 0.14, excuse me, and that's 49. And then I know that 67% of that original brightness is blue. And I get 234.5. If this number had been over 255, I would have to cap it at 255, okay? So now, of course, all right. So, of course, these are non-integer values, so I would probably truncate them or round them or whatever you want to do. So I'll just truncate them. 66, 49, 234. Okay, so this is the average, or this is the reconstructed Pixel 1. Now, is it the same as the original? Let's look at the original Pixel 1. Was 100, 50, 200. Okay, so I can see that the last two pixels are really quite close. 49 versus 50, 200 versus 234. The first pixel is quite a bit off. But so what that means, because it's not exactly the same, this is a lossy compression algorithm. Okay, you reconstruct pixel 2. Similarly. Okay. So in the code, in the assignment today, you guys are going to actually run this algorithm to compress an image of the cat Ivan. Okay? So I'll actually show you a little bit more about how this works in the Zoom room, and I will meet you there momentarily. Okay?